Vibration analysis, signal processing, sampling and aliasing, understanding waveform conversion and frequency distortions. Understanding sampling the signal and sample rate. Sampling is the process of converting a continuous analog vibration signal into a digital format that can be analyzed by modern vibration analyzers. The analog signal from a sensor contains all vibration information across a range of frequencies. To digitize this signal, the analyzer takes discrete measurements called samples at regular intervals. The number of samples taken per second is known as the sample rate, fs. The sample rate determines the highest frequency that can be accurately measured, referred to as Fmax. According to the Nyquist theorem, the sample rate must be greater than twice the highest frequency of interest to avoid aliasing. In practice, analyzers often use Fs equals 2.56 times Fmax to provide a safety margin and compensate for imperfect filters. For example, if the highest frequency of interest is 1000 Hz, the sample rate should be at least 2560 samples per second. Proper sampling ensures that the waveform accurately represents the machine's vibration behavior and provides the foundation for accurate spectral analysis. Aliasing phenomenon and its prevention. Aliasing occurs when the sampling rate is too low to capture the true frequency content of the vibration signal. When this happens, high-frequency components appear as false low-frequency signals in the spectrum, leading to incorrect diagnoses. A common analogy is the strobe light effect on a rotating wheel, where the wheel appears stationary or moving backward when the strobe flashes too slowly. To prevent aliasing, the Nyquist criterion requires that Fs greater than 2 times Fmax. However, due to real-world limitations such as filter imperfections, vibration analyzers typically sample at Fs equals 2.56 times Fmax. Additionally, anti-aliasing filters are applied to remove frequencies above Fmax before digitization. These filters ensure that unwanted high-frequency energy does not distort the spectrum. Understanding aliasing is critical because misinterpreted data can lead to incorrect maintenance decisions and unnecessary downtime. Role of FFT in signal processing. The fast Fourier transform, FFT, is a mathematical algorithm that converts a time-domain waveform into a frequency-domain spectrum. This transformation is essential because the time waveform often contains complex overlapping signals that are difficult to interpret. The FFT decomposes the waveform into its constituent sine waves, each represented by a frequency, amplitude, and phase. For single-channel measurements, phase information is typically discarded, leaving amplitude versus frequency for analysis. The FFT requires a specific number of samples, usually a power of 2, for example 1024, 2048, 4096, and outputs n divided by 2.56 spectral lines, where n is the number of samples. This process allows analysts to identify forcing frequencies, harmonics, and sidebands that indicate specific machine faults. Without FFT, diagnosing complex vibration patterns would be nearly impossible. Sampling and resolution, impact on diagnostic detail. Resolution in a vibration spectrum refers to the smallest frequency difference that can be distinguished between two adjacent peaks. It is calculated as R equals Fmax divided by LR, where LR is the number of lines of resolution. Higher LOR values result in smaller R, meaning better detail and the ability to separate closely spaced frequencies. For example, if Fmax equals to 1000 Hz and LR equals to 400, the resolution is 2.5 Hz, increasing LR to 800 improves resolution to 1.25 Hz. However, higher resolution requires more samples and longer acquisition times, creating a trade-off between detail and practicality. Analysts must balance the need for fine resolution against the time available for data collection. Poor resolution can mask critical fault frequencies, while excessive resolution may slow down testing unnecessarily. Understanding sample time, T. Sample time, T, is the duration required to collect the necessary number of samples for a given resolution and Fmax. It can be calculated as T equals to LR divided by Fmax. For example, if Fmax equals to 100 Hz and LR equals 12,800, the sample time is 128 seconds for one average. Longer sample times improve resolution but increase test duration, which may not be practical in routine monitoring. Analysts must consider machine operating conditions and time constraints when setting sample time. Collecting sufficient data ensures accurate FFT results and reliable fault detection, but excessive sample times can lead to inefficiencies in data collection routes. Relationships between parameters. Sampling and spectral analysis involve interconnected parameters that define data quality. Key relationships include Fs equals to 2.56 times Fmax, N equals to 2.56 times Lr, R equals to Fmax divided by Lr, and T equals to 1 divided by R. These formulas link the time domain waveform and frequency domain spectrum, ensuring consistency in data acquisition and analysis. Understanding these relationships helps analysts configure their instruments correctly to achieve the desired balance between resolution, accuracy, and efficiency. Misconfigured settings can lead to poor resolution, aliasing, or incomplete fault detection. Therefore, mastering these concepts is essential for reliable vibration analysis and predictive maintenance.